So I'm going to move on. Eric's mentor is in a car and may or may not have service. I do have something from him, Dr. Feradas, if you are not able to join. So, Christian, do you want to try to join?
I don't.
Yes, hi, can you hear me?
Yes.
I can hear you.
Okay, perfect. So my name is Christian Ferradas from NASA Goddard, and I've been working with Eryk for the last several weeks, and it's been a pleasure working with him. I've been amazed at his determination, at his enthusiasm for the research we've been doing, and for how he has found solutions very creatively to all the problems that we found. And we've been working on studying the radiation environment in the near Earth space, which is very important for space weather. So I really hope that Eryk has enjoyed doing this work, and I'm sure he'll use all of the lessons that he has learned in his future projects. So I'm quite happy with how the work came out. And yeah, I'll let you now hear from Eryk himself about his work.
Are you ready for me to start presenting?
Yes. Go ahead.
Yes.
I'll put on a timer. I'll put on a timer.
Thank you.
We have a little more flexibility today, luckily, since there's only one
Good,
more after you,
because
Eryk.
every time I tried presenting, I did a practice. It took like 10 minutes.
Okay.
That's
You
okay.
did well the other day on Wednesday. It was pretty
Yeah.
compact. Go ahead.
Okay. I'm ready. Hi, my name is Eryk Kaczocha, and this is my project on the comparison of the peak fluxes of protons between the geostationary and low Earth orbits. Okay, so solar energetic particles, which are what we're measuring the flux of, those are released electrons, protons, and alpha particles that come from the sun. They have varying levels of energy, with most of them being between 1 MeV, which is 10 to the 6th electron volt, and 100 MeVs, which is 10 to the 8th electron volt. What we're going to be measuring is called particle flux, which is a measure of the number of particles passing through a channel on a satellite, which is equal to the particles per steradian times second times centimeter squared of the channel. Oh. So here's a figure to help you understand what we're doing here. So we can see when there's a lot of SEPs about to be released, because they don't get released at a static rate. They increased in some conditions. That's when the magnetic field intensifies and magnetic potential energy gets stored. And then it causes a blast of energy called a solar flare, and then later on a coronal mass ejection forms, which is what we're going to talk about. Oops. So solar flares are shock waves of solar waves and particles heading outwards from the sun. Their intensity has a strong correlation with the amounts of energy released at lower temperatures. That means the number of SEPs that get released. And then coronal mass ejections are just what they sound like, huge ejections of mass from the core of the sun, which leaves the sun and heads outwards. The speed of a coronal mass ejection has a strong correlation with the amount of energy released at higher temperatures. So now, the Earth's magnetic field protects it from the surface, protects its surface from the SCPs that are incoming, and it deflects them away from the Earth so it doesn't hit. So while it keeps all life on Earth safe during SCP events like solar flares or coronal mass ejections, those events are still harmful to humans by damaging satellites that are not protected by their magnetic field because they're too far out, shutting down radio communications by damaging those satellites, and potentially being harmful to astronauts. Now, those magnetic particles, those particles that get deflected by the magnetic field, the SCPs, will end up in one of two Van Allen belts. Those are radiation belts that are filled with energetic particles, including SCPs, that get caught by the Earth's magnetic field and they typically form between the GEO and LEO, geostationary and low Earth orbits. However, it is possible sometimes for the upper Van Allen belts to actually cross through GEO, and for GEO to actually be in the upper Van Allen belt. And there's usually two, the upper, the outer, and the inner. But during some space weather events, including SCP events, it's possible for a third Van Allen belt to form. So here's our research question. We're going to be discovering, is there a correlation between the energetic ions, including SCPs, detected at GEO with those detected at LEO? So starting off for my methodology, in order to measure the correlation, we need to use data from collection devices to compare the proton peak fluxes at GEO and at LEO. And those are devices, those collection devices are on satellites that we'll be using. The first satellite we'll be using is at GEO. It's called GOES, stands for the Geostationary Operational Environmental Satellite, and it remains in a geostationary orbit, meaning that its period of orbit is the same as the period of the Earth's rotation, so it always stays above the same area of land. And that is also past the Van Allen belts, both of them. However, it's, again, as I said before, it could sometimes be up in the upper Van Allen belt, the outer one. So GOES will detect the SCPs before they get reflected by the Earth's magnetic field into one of the Van Allen belts. Because it's above the inner Van Allen belt, however, GOES cannot detect any precipitated particles out of the Van Allen belt. That's important. The second satellite we're using is called the International Space Station, which is in low Earth orbit, which is below both Van Allen belts, so it's protected from all the SCPs, and it kind of has to be because there's astronauts aboard it, which can make it extremely dangerous if it's above the Van Allen belts. And because of its location, it will only detect particles that made it through the Van Allen belts and weren't deflected by the magnetic field. But it can also detect the particles that have been precipitated out of the lower Van Allen belt, the inner one. So now, the proton flux value data from those two satellites, the GOES and the ISS, are going to be compared in order to determine the correlation between the energetic particles measured at GEO and at LEO during the SCP events. So here are my data sources. For GOES, the graphs have been provided, but for the ISS, the graphs have not been provided. I had to make them from the data that was provided. So the ISS data also had a lot of extraneous stuff beyond just SCP flux. So therefore, I had to write Java code in order to take in the ISS data files and release only the dates and the proton and electron data. This data was outputted by the program and inputted into Microsoft Excel, so I could make the line graph, which can be compared to the graphs provided by GOES. So here's a brief description of my program and how I used it. The ISS data files had to be renamed data.txt for it to work in the program, all lowercase. And then I had to put in all the integers 0 to 3, 0 to provide the electron data, 1 to provide the low energy proton data. That means below 3.75 times 10 to the 6th electron volts. 2 to provide the high energy proton data, meaning above 3.75 times 2 to the 6 times 10 to the 6th electron volts. And 3 providing the dates. Then now I'll just have a brief description of how it works. The main method in main.java runs, which requires the dates and stores them in an array list, and then runs the buffered file writer methods in mains.java. So basically, the buffered file writer method takes in all the information from the text file that we need and outputs them onto two different text files, proton.txt and electron.txt, which have all the data that we can copy and paste into Microsoft Excel and graph. So here we'll have an example of one individual ISS data point before and after being processed. So we can see here the original data and contain a lot of extraneous stuff that we don't need. And then I put it into the program and output it, it becomes a lot more organized and something that's much easier to graph. And now there's hundreds of thousands of data points because data points were taken every 10 seconds by the ISS. And each of the SEP events that we'll be measuring is going to cover 3 days. So hundreds of thousands, maybe even millions of data points. So here's my Java code that I wrote. Okay, so here's our first comparison. We can see that, try to make it easier to see. We can see that for the SEP event in June 2015, in June, sorry, March 2013, I'm so sorry. We can see that the GOES data started to increase until March 17th, 2013, and then started to decrease after that. And then on the ISS data, we could kind of see that it started increasing until March 17th, 2013. But then after that, even it spiked and it still is stayed relatively high, showing that there's a weak correlation between those two. We could vaguely see a correlation, but not very much so. So now here's the SEP event that happened in June 2015. This is the one I was confusing it with. So we can see that the GOES data started slowly but decreasing until June 21st, 2015. And then it started spiking, and then towards the end of June 22nd, 2015. The ISS, with the ISS data, we could vaguely see that started declining, but then started increasing a little, but then it only really started spiking towards the very end of June 22nd, 2015, which is another weak correlation that was shown. So now, both these SCP events showed a weak correlation between the GOES data and the ISS data. Here's the most probable explanation for it and what we could learn from this data comparison. As I said before, particles precipitated from the lower Van Allen belt were only detected by the ISS. GOES was too high up to detect them, and that could be the probable source of the extra particles that were seen at the ISS but were not seen at GOES. And then for the particles that were seen at GOES but not the ISS, the reason why that was so fluctuating is because the Earth's magnetic field strength probably varied in intensity. And when the magnetic field was weaker, there was probably a stronger correlation, as more particles that were detected by GOES could have made it to the ISS and gotten detected. But then there could have been weaker correlation when the Earth's magnetic field was stronger, and therefore most of the particles that reached GOES would not have hit the ISS and would have gotten deflected into one of the Van Allen belts, which could have caused and these could have caused the weak correlation that we've seen. And in conclusion, I'd like to give a big thank you to my mentor, Dr. Chris Ferradas, who made this project possible, and the N3 program. I really appreciated it. I really like it. I really like this a lot. I like doing this project a lot. He would like to also give a huge thank you to NASA for providing the graphs for GOES and the data for the ISS so we can make this comparison and make this project possible. And there it is.
All right, good job, Eryk.
Really good.
Thank you.
I think the physics involved in this understanding what's going on with all these particles in the Van Allen belts is very complicated.
Anyone's got any questions?
So it's a very impressive project because that's a lot of
Thank you.
plasma physics, really.
Thank you so much.
Anyone want to ask Eryk a question?
I know I already asked him my question during the practice, though.
Oh, yeah. All right.
So
Okay.